Today we're setting up a brand new project in Code Orchestra to show you all of the different features available in this pre-alpha build. First thing we want to do is to create a new project in Unreal Engine 5. We're going to be using C++ template. So here's our brand new project. You can see there's absolutely nothing extra in it, just out of the box template, working as expected. The first thing we're going to do is we're going to set up the project for Code Orchestra. So once we have all of the tooling installed, we just navigate to our new project directory. We call our composer tool, and we let it know that we'd like to set up the project for Code Orchestra integration. We will enhance the tooling to do this next part automatically upon initial setup, but right now we're just going to build it so it generates all of the default templates that come out of the box. Once it has built, we're going to go ahead and open the project in Unreal Engine 5 all over again. We're going to let it rebuild. And then we're going to go ahead and just play. You can see right away that we have the default template that came with Code Orchestra, injecting a log that's letting us know that C# was loaded and our welcome script ran. To modify the script, we can jump into the Code Orchestra provided solution, which will contain all of our managed C# code. Here we could see the line that said hello from C#. We're going to add an additional log. We basically piggyback off of the Unreal Engine logging system. So anything you write here will make it into the stack. You go ahead and log a warning. We're going to rebuild the project using the Build Code Orchestra button in the tooling. You could also do it from command line. Then you saw that the project automatically refreshed, hot reloaded all the code. There's our brand new log. So now let's do something a little bit more interesting. Let's add some functionality so we can manipulate some of the objects inside of the game. We're going to create what we call behavior. It's essentially a scene component you could add to other scene components. We're going to expose a property here called move speed. This will allow us to expose this to the Unreal Engine editor and will allow us to use the value to move whatever object we attach our behavior to up in the Z axis. So once we build Code Orchestra, rebuild the project, we're going to essentially attach our test behavior to one of the cubes inside of the scene. And once we attach it, we can see our UProperty being exposed inside of our test category. And we're going to tell it move speed of 100. Let's enhance this a little bit further. Let's go ahead and add a Boolean property, which allows us to toggle the logic on and off, just so we could see that the editor and the logic reads this in real time. So after a quick rebuild, we could go back in the editor, and we can see that our new Boolean property is being exposed. Let's take this one step further. Let's create an UEnum and expose the UEnum in the editor. So we'll call it move speed, and then we'll allow the user to either have slow, fast, or a custom speed that they said inside of the move speed property. We'll rebuild, and after a quick rebuild again, it'll now be available as an UEnum inside of the editor. So once again, we go down to our test behavior, and then we could see our enum. We could swap it slow, fast, or custom. Next, let's go ahead and create a prefab that we can instantiate from code. We'll create a prefab directory, and then we'll create a blueprint. I'm going to go ahead and call it test prefab, and just create a simple cube here that we can use just to visualize the prefab instead of the scene. We'll add the same test behavior as before, that way we have some movement on all of these prefabs. Turn movement on. And there's the code. We can load prefab via assets.loadPrefab, and we're just going to simply call world.spawnAt, provide position and rotation information. I'm going to go ahead and rebuild the code. We're also going to move the prefab directory. I had it nested accidentally one under. There we go. Now when we play, we can see all the prefabs are loaded by the code on startup. Let's go ahead and change the scale of the cube. That way we can visually see their individual objects. We'll change it to 0.75 scale. And now when we play the scene again, we can see they are individual objects being loaded. So what about integrating with existing components, third parties, other code, whether it's blueprints you've written? Well, here we go. Let's copy over a third-party component, Ultra Dynamic Sky, and we'll open up one of the default maps it comes with. We can see here the map is working. And we could go ahead and access the Ultra Dynamic Sky blueprint. We could go down to time of day, and in the editor we could set the time of day by changing the value of the property. Just to confirm, the exposed name of the property is time of day. It's a float. So we want to go ahead and modify that from our script so we could drive logic inside of this third-party blueprint. We're going to create another behavior, and this behavior will essentially get a reference to our Ultra Dynamic Sky blueprint, and then it will set one of the properties. Here we could see we're getting a reference to the parent of our behavior, and then we're calling setFloat, time of day, and we're modifying that. We're simply incrementing that by 100 every second. And don't forget to add the behavior to the blueprint. And there we are. You can see time of day being incremented by C# code cleanly. So, how can you actually debug the code? You can either attach directly from Visual Studio by selecting Unreal Editor, and you can see we have full access to all of the methods in memory you would expect. Or we could drop a line of code anywhere, simply telling the debugger to attach. Don't forget, you could have a compiler attribute, which allows you to only call this line in debug mode and not in release mode. There we are, the debugger attached, and we can go ahead and breakpoint just like you would expect. Once again, full access to all of the variables. Here we can see that we have full access to the scene hierarchy. So you could walk the parents, all the children's, you could query based on names. And when you're debugging, you can see you have full access to the entire class and all of the data. Because of the way we integrate with Unreal Engine, all of the data comes from shared memory from all of the C++ classes. Let's try some simple logic with some raycasting. Let's build a raycaster behavior that shoots a ray and detects anything in the world dynamic channel. We're going to go ahead and attach it to our player. And we're just going to log to the screen to ensure that we have an easy way to determine whether or not we're casting on something. There we are. We can detect hits. Next, let's try to use a data-oriented approach. We're going to use Presto ECS, another library that we provide, and it's an ECS that can be plugged into Unity or Unreal. We're simply going to expose the ECS system in our main class for now, and attach a few bootstrapping calls that need to occur during the life cycle of the game engine ticks. Once we have the system hooked up in the main class, we're going to go ahead and create a folder for our components so we could create a component. We're now going to create a transform component, which can store the position and rotation of entities. Next, let's go ahead and create a folder for systems so we could define different systems. And now we're going to create a test system that simply moves anything that has a transform component up on the z-axis by 100 centimeters every second. It's essentially replacing the logic we had in the behavior before, but turning it into a system. Now we're going to actually instantiate our ECS system, and we're going to add our new test system to the sync update stage. Finally, we're going to modify the test behavior, which was previously responsible for moving the object, into a shell that simply creates a brand new entity and attaches our transform component to it. And we want to make sure we initialize the system before we actually load any prefabs. So the system creation occurs first. Once we build code Orchestra, we can see that there we are. We're moving transforms using our ECS logic. We can see here that inside the system, the simple loop iterates over all transform components and modifies their position. We can absolutely make this multi-threading friendly by changing our architecture a little bit and the way we actually read and write data from Unreal Engine scene components. Code Orchestra also ships with the job system. So you could go ahead and queue a synchronous or asynchronous job. You could await on frames or wait for a specific amount of time. Code Orchestra ships with an optional input system. Here, we're going to bind the input system to any key being pressed on the keyboard. This will allow the system to monitor and capture the Unreal Engine events being emitted. We're going to create a class that represents a menu system, which can consume the U key. Whenever the menu is turned on, it will consume other keys, so subsequent systems will not be able to act on them. Here, we're going to capture the left mouse being pressed unless we toggle the menu on and off via the U key. Once deployed, we could see that the system captures the left mouse unless we toggle the menu on. Code Orchestra is built to not only offer a comfortable, familiar, and well-integrated development experience for C# developers, it is built to perform. In this lightweight benchmark, we've created a C++ actor which updates its relative location X amount of times every single frame. We have done the same exact thing in C#, where we update the relative position of a scene component an X amount of times per frame. As we fire off the scene, we can navigate to the actor and modify the iteration count in C++ to 1,000,000. This means that the relative position will be updated 1,000,000 times a second to introduce artificial overhead. We could see here that we hit about 30 milliseconds per frame. As we switch over to our C# component and update the relative position of the scene component 1,000,000 times per update loop, we can see that the performance is about 31 milliseconds. We are calling the native Unreal Engine C++ relative position update function over 30 million times a second at the cost of only 1 millisecond or 3% overhead when compared to writing native C++ code in Unreal Engine.